Okay, continuing on with chapter 10, we've been talking about the ion dipole type of intermolecular interaction. So as an example of how we can use this to kind of evaluate some different types of chemical processes, if we look at a reaction like this reaction here, where we're taking a sodium cation in the gas phase, introducing it to water, this will cause a series of interactions between the positively charged sodium ions and the negative ends of the polar water molecules to make a hydrated cation, which we see on the product side there. So Na with 6 waters around it, and it's still got a positive charge. The enthalpy associated with this particular reaction, or the change in enthalpy of formation, is minus 405 kilojoules per mole. So remember, the negative for enthalpy change means energy is being released. So there's some bonding going on, some interactions at least between the sodium cation and the water molecules, right? And the enthalpy change here is an interaction is a measure of how strong those interactions are. Now, what we want to think about is, based on that value that we have now for this reaction involving a sodium cation, how would we expect things to be different for a potassium cation? So how would the interaction that happens, the association of the cation with the polar molecules, how would that be different for potassium? So let me give you the value, and then we can talk about how we might have been able to arrive at that conclusion. The enthalpy change for hydration of a potassium cation is minus 312 kilojoules per mole. Okay, so this is less than what we see for sodium. Now, how can we understand why this should be a reasonable expectation that that is a lower value for the enthalpy of that reaction? The biggest difference here is not charge, like we saw in the previous examples, because the sodium cation has +1 charge, so does the potassium cation, and the molecule that it's interacting with, in both cases water, is the same as well. The difference here is going to be the distance. Potassium is one row below sodium in the periodic table. So potassium cation is a fair bit bigger than a sodium cation. So as a result, the distance between kind of center of the positive charge, the center of the potassium cation, is going to be further away from the partial negative charge on the water molecule. Well, they're further away. We know that that's going to be on the bottom of the fraction in our Coulomb's law relationship. So the interaction is not going to be as strong. And we see that reflected in the enthalpy. If we aren't forming as strong of an interaction between the cation and the water, there's not going to be as big of a change in energy, or the enthalpy of the reaction. Right? We should be able to draw a similar conclusion with lithium. Now, what's different with lithium is one row above sodium in the periodic table. So a lithium cation is smaller than a sodium cation. Well, if it's smaller, that means it's going to be able to get closer to the water molecules. So the distance in this case is going to be lower, but a smaller number on the bottom of a fraction, that's going to give us a bigger force. And we see that in the enthalpy for hydration for lithium. The enthalpy of hydration for lithium is negative 515 kilojoules. So even more energy is released when lithium interacts with water, because the lithium has a stronger interaction with the polar water molecules. Now, if we move to magnesium, right, now we've got two things changing. The size of the magnesium cation is changing, but also the charge is changing. What we see for the enthalpy of hydration for a magnesium cation is that it's much larger. Much larger in magnitude. It's actually a negative number, so it's not technically larger. Minus 1,921 kilojoules. So this is a function not only of the charge. We now have a +2 cation instead of a +1 cation, so that's going to increase the strength of the interaction, or increasing the numerator of that fraction we talked about in terms of Coulomb's law. A +2 cation is also significantly smaller than a +1 cation. Remember, every time we take an electron out of a particular electron configuration, the remaining positive charge at the nucleus can contract what's left of the electron cloud. So the +2 cation gets even smaller. So not only is this a stronger interaction in terms of charge, but the magnesium can get even closer to the water, leading to a much stronger interaction. And again, all this goes back kind of to the first principles of our understanding of structure and what is the charge, how strong is the polarity of the molecule, and how are these pieces going to interact. Okay. Now, moving on to another example. The next type of interaction we want to talk about is called a dipole interaction. So as you might imagine, this is the interaction between two polar molecules. So we can use this to get a handle or an understanding on what kind of physical properties would we expect based on the structure of a particular molecule. And to kind of highlight some of what we're looking at here, I have a couple of comparisons here. So on one hand, this is going to give us an opportunity to kind of review a little bit about drawing Lewis structures, which is going to be very important for this chapter in particular as we're evaluating these intermolecular interactions, but a good review overall as well. So the first comparison, I'm going to look at N2, or nitrogen, and carbon monoxide, or CO. Now if I go to draw the Lewis structure for nitrogen, there's just two nitrogen atoms, so they would be connected by a covalent bond. This would leave 8 valence electrons, 5 from each nitrogen, so that would be 10 total. If I draw in those 8, I would get a structure that looks kind of like that. Now, we wouldn't be particularly happy with that structure because we have not satisfied the octet rule. Remember, that's the first thing we want to think about. So what I'm going to end up doing here is sharing a pair of electrons from each of the nitrogens into the bonding between the nitrogens. That would get both nitrogens up to the position where they have 8 electrons, satisfy the octet rule, and that would be a good structure for the diatomic nitrogen molecule. Now, since nitrogen has the same electronegativity as nitrogen, the two components here, this is going to be nonpolar. So this is not a polar molecule. And if it's nonpolar, it doesn't have a negative side and a positive side. So if it doesn't have a negative side and a positive side, it won't have dipole-dipole interactions. And that will be something we need to think about in terms of what are its physical properties going to be. Now, the difference here is carbon monoxide. It's also just 2 atoms, so they would be connected by a line in between them. Now, in this case, though, there's 8 electrons remaining. Because oxygen is more electronegative than carbon, it would be smarter to put as many electrons on oxygen as we could before we start moving them around. So I'm going to put 6 electrons on the oxygen. The last 2 have to go on the carbon because, of course, oxygen can't have more than 8 electrons in its structure. But this, however, would lead us to the same type of structure as we saw for nitrogen. We'd end up having to share because the oxygen, while oxygen has 8 electrons, carbon is deficient. It only has 4 here, so we share to get the carbon up to satisfying the octet rule. And that would give us a structure that's pretty similar to nitrogen in that there's a triple bond between the atoms and then there's 2 non-bonding electrons on each atom. Now, formal charge is something you should also be familiar with as well, because that is a good way to evaluate not only the stability of the structure that you drew, but also its reactivity. Carbon, in this case, carbon starts with 4 valence electrons. In this case, there are 3 bonds to the carbon and 2 non-bonding electrons. So to calculate the formal charge would be 4 for the number of valence electrons, minus 3 for the number of bonds, minus 2 for the number of non-bonding electrons. This molecule actually has a negative formal charge on the carbon atom. Oxygen is in a similar bonding arrangement, but oxygen has 6 valence electrons. So for oxygen, this would be 6 minus 3 minus 2. That means a positive charge on the oxygen. Now, carbon monoxide is a little bit of a tricky situation in terms of polarity